The National Electrical Code does not specify a maximum length difference for paralleled conductors. However, there are some generally followed guidelines. A length difference of less than 3% is generally considered acceptable for most applications. A difference of 3 to 5% may cause some concern, but it's typically not a significant issue. A length difference greater than 5% can lead to uneven current distribution and potential overheating. There are consequences of length differences. Firstly, uneven current distribution means longer conductors carry less current than shorter conductors. Secondly, heating can occur where the longer conductors carry more current for a given load, which can lead to overheating. Thirdly, expansion can occur where the longer conductors may expand more than the shorter conductors, causing slack in the conduit or panel board. Fourthly, length differences can cause voltage drop variations between paralleled conductors. Measuring conductor length in conduit can be challenging. Here are some methods. Firstly, a pull string can be used by pulling a string through the conduit and measuring its length. Secondly, a laser distance meter can be used to measure the length from the conduit entrance to the pull box. Thirdly, if the conductor is on a reel, measure the circumference of the reel and count the number of revolutions the conductor makes, then multiply the circumference by the number of revolutions to get the approximate length. Fourthly, some conductivity testers have a distance measurement function that can measure the distance between 2 points in a wire. If the length difference is unavoidable, use a larger conduit size to allow for expansion. Secure the conductors firmly at all termination points to prevent slack and movement. Monitor the circuit regularly for signs of overheating. It is important to note that proper installation and adherence to the National Electrical Code are crucial for safe and efficient operation of electrical systems using paralleled conductors. Uneven current distribution can occur when paralleled conductors have different lengths or impedances. The shorter or lower impedance conductors will carry a larger share of the current, potentially overloading them and causing overheating. This can lead to premature failure of the conductors and increase the risk of electrical fires. To mitigate the risk of uneven current distribution, it is essential to use conductors of the same length, size, material, and insulation type when paralleling. Additionally, all conductors should be installed in the same raceway or cable tray to ensure that they experience the same ambient temperature and magnetic fields. The National Electrical Code provides specific requirements for paralleling conductors in Section 310.10. These requirements include the minimum size of conductors that can be paralleled, the need for all conductors to be the same length and have the same electrical characteristics, and the requirement that the overcurrent protection device be sized to protect the smallest conductor in the parallel set. When paralleling conductors, it is also important to consider the ampacity dirting factors specified in the National Electrical Code. These dirting factors may be necessary when multiple conductors are installed in the same raceway or cable tray, as the heat generated by the conductors can reduce their ampacity. In addition to the length and impedance of the conductors, the termination methods used can also affect current distribution. Poorly made or loose connections can create additional resistance, causing more current to flow through the other conductors in the parallel set. Therefore, it is crucial to use proper termination techniques and ensure that all connections are tight and secure. Voltage drop is another important consideration when paralleling conductors. Voltage drop is the reduction in voltage that occurs along the length of a conductor due to its resistance. Excessive voltage drop can cause equipment to operate inefficiently or fail to operate at all. To minimize voltage drop, it is important to use conductors of sufficient size and to keep the length of the conductors as short as possible. The National Electrical Code provides guidelines for calculating voltage drop in Section 215.2. These guidelines can be used to determine the appropriate conductor size for a given application. When paralleling conductors, the voltage drop will be the same for all conductors in the parallel set, as they are all connected to the same source and load. However, if the conductors are not of the same length or impedance, the current distribution will be uneven, which can affect the overall voltage drop in the circuit. Therefore, it is important to ensure that all conductors are of the same length and have the same electrical characteristics to minimize voltage drop and ensure proper operation of equipment. In some cases, it may be necessary to use a larger conductor size than would otherwise be required to compensate for voltage drop. This is particularly true for long runs of conductors or when the load is located far from the source. The National Electrical Code provides tables that can be used to determine the appropriate conductor size for a given voltage drop requirement. These tables take into account the length of the conductor, the current flowing through the conductor, and the conductor material. In addition to the electrical considerations, there are also mechanical considerations to keep in mind when paralleling conductors. The conductors must be supported properly to prevent them from sagging or coming into contact with each other. The National Electrical Code provides guidelines for supporting conductors in Section 314.27. These guidelines specify the maximum spacing between supports and the type of support that should be used. When paralleling conductors in a conduit, it is important to ensure that the conduit is large enough to accommodate all of the conductors. The National Electrical Code provides tables that can be used to determine the appropriate conduit size for a given number of conductors. These tables take into account the size of the conductors and the type of conduit being used. It is also important to ensure that the conduit is properly supported to prevent it from sagging or coming into contact with other objects. In addition to the National Electrical Code requirements, there may also be local codes or regulations that apply to paralleling conductors. It is important to check with the local electrical inspector to ensure that all applicable codes and regulations are being followed. Paralleling conductors can be a complex topic, and it is important to have a thorough understanding of the electrical and mechanical considerations involved. If you are not comfortable working with electrical systems, it is best to consult with a qualified electrician. When dealing with parallel conductors, several factors can influence their performance and safety. Firstly, the length of the conductors plays a crucial role. Ideally, all parallel conductors should be of equal length to ensure that the current is evenly distributed among them. Unequal lengths can lead to imbalances, with shorter conductors carrying a disproportionately larger share of the current. Secondly, the size or gauge of the conductors is also important. All parallel conductors should be of the same size to ensure that they have the same ampacity and impedance. Using different sizes can result in uneven current distribution and potential overheating of the smaller conductors. Thirdly, the material of the conductors, typically copper or aluminum, should be consistent across all parallel conductors. Different materials have different conductivity properties, which can affect current distribution and overall circuit performance. Fourthly, the insulation type of the conductor should be the same for all parallel conductors. Different insulation types have different temperature ratings, and using mismatched insulation can lead to premature failure of the conductors due to overheating. Fifthly, the termination methods used to connect the parallel conductors should be consistent and properly executed. Loose or corroded connections can create additional resistance, causing more current to flow through the other conductors in the parallel set. Sixthly, the ambient temperature in which the parallel conductors are installed can affect their ampacity. Higher temperatures can reduce the ampacity of the conductors, so it is important to consider the ambient temperature when selecting the appropriate conductor size. Seventhly, the proximity of other conductors or heat sources can also affect the ampacity of parallel conductors. Installing conductors too close together can increase their operating temperature and reduce their ampacity. Eighthly, the type of raceway or conduit in which the parallel conductors are installed can affect the heat dissipation. Enclosed raceways can trap heat, while open raceways allow for better ventilation. Ninthly, the dirting factors specified in the National Electrical Code should be applied when multiple conductors are installed in the same raceway or cable tray. These dirting factors account for the reduced ampacity of conductors due to heat buildup. Tenthly, the overcurrent protection device, such as a circuit breaker or fuse, should be sized to protect the smallest conductor in the parallel set. This ensures that the conductors are protected from overloads and short circuits. 11thly, regular inspection and maintenance of parallel conductor installations are essential to identify and correct any potential problems, such as loose connections or damaged insulation. 12thly, documentation of the parallel conductor installation, including conductor sizes, lengths, and termination methods, is important for future reference and troubleshooting. 13thly, training of personnel involved in the installation and maintenance of parallel conductor systems is crucial to ensure that they understand the relevant codes and standards and can perform their duties safely and effectively. 14thly, coordination with the local utility company is important to ensure that the parallel conductor installation meets their requirements and does not interfere with their distribution system. 15thly, consideration should be given to the potential for future expansion of the parallel conductor system. It may be necessary to install larger conductors or raceways to accommodate future load growth. 16thly, the use of appropriate tools and equipment is essential for safe and efficient installation and maintenance of parallel conductor systems. This includes wire strippers, crimpers, torque wrenches, and insulation testers. 17thly, the implementation of a quality control program can help to ensure that the parallel conductor installation meets all applicable codes and standards and is free from defect. 18thly, the use of surge protection devices can help to protect parallel conductors from damage caused by voltage surges and transients. 19thly, the grounding and bonding of parallel conductor systems should be properly implemented to minimize the risk of electric shock and ensure the safety of personnel and equipment. 20thly, the use of appropriate labeling and signage is important to identify parallel conductor systems and provide information about their voltage, current, and other relevant parameters. In addition to the factors mentioned above, there are also some specific considerations for paralleling conductors in different types of applications. Firstly, in hazardous locations, such as those containing flammable gases or vapors, special precautions must be taken to prevent explosions or fires. The National Electrical Code provides specific requirements for wiring in hazardous locations in Articles 500 through 516. Secondly, in healthcare facilities, special attention must be paid to the grounding and bonding of parallel conductor systems to minimize the risk of electric shock to patients and staff. The National Electrical Code provides specific requirements for wiring in healthcare facilities in Article 517. Thirdly, in data centers, parallel conductor systems are often used to provide redundant power to critical equipment. In these applications, it is important to ensure that the conductors are properly sized and protected to prevent downtime. Fourthly, in industrial facilities, parallel conductor systems are often used to supply power to large motors and other heavy loads. In these applications, it is important to consider the starting current of the motors and to select conductors that are capable of handling the inrush current. Fifthly, in renewable energy systems such as solar and wind power installations, parallel conductor systems are often used to connect multiple sources of power to a common bus. In these applications, it is important to ensure that the conductors are properly sized and protected to prevent overloads and short circuits. Paralleling conductors is a common practice in electrical systems, but it is important to understand the potential risks and to take appropriate precautions to ensure the safety and reliability of the installation. The National Electrical Code provides comprehensive guidance on the proper installation and maintenance of parallel conductor systems. Consulting with a qualified electrician is always recommended when working with electrical systems. When considering the ampacity of parallel conductors, the National Electrical Code provides specific guidelines in Section 310.10. The ampacity of each individual conductor must be derated according to the number of conductors in the raceway or cable. This derating is necessary to account for the heat generated by the conductors, which can reduce their ability to carry current safely. The derating factors are specified in Table 310.15b3 of the National Electrical Code. For example, if there are 4 to 6 current-carrying conductors in a raceway or cable, the ampacity of each conductor must be derated to 80% of its original value. If there are 7 to 9 current-carrying conductors, the ampacity must be derated to 70%. It is important to note that these derating factors apply only to current-carrying conductors. Grounding conductors and equipment grounding conductors are not subject to these derating requirements. In addition to the derating factors, the National Electrical Code also requires that the conductors be sized so that the calculated load does not exceed the adjusted ampacity of the conductors. This calculation must take into account all applicable Dartington factors, as well as any other factors that may affect the ampacity of the conductors, such as ambient temperature and conductor insulation type. When paralleling conductors in different raceways, it is important to ensure that the raceways are bonded together to provide a common ground path. This bonding is necessary to prevent circulating currents from flowing between the raceways, which can cause overheating and other problems. The bonding jumpers should be sized according to the requirements of the National Electrical Code and should be installed in a manner that provides a low impedance ground path. When using aluminum conductors, it is important to use connectors that are specifically designed for use with aluminum. Aluminum connectors are typically made of aluminum alloy and are coated with a corrosion inhibitor to prevent oxidation of the aluminum. Copper connectors should not be used with aluminum conductors, as this can lead to galvanic corrosion, which can weaken the connection and cause it to fail. When making connections to parallel conductors, it is important to use proper torquing techniques to ensure that the connections are tight and secure. Loose connections can create additional resistance, which can cause overheating and other problems. Torque wrenches should be used to tighten the connections to the manufacturer's specified torque values. After the connections have been made, they should be inspected to ensure that they are properly installed and that there are no signs of damage or overheating. Regular inspections should be performed to identify any potential problems before they become serious.